Assalamu alaikum. So inshallah, we're going to start our first recorded lesson with combinatorics. And for the GRE, combinatorics just really means the math of decisions or choices. So inshallah, be patient with me. It's my first time doing this on a recording, but inshallah, it won't be too bad. So if we look at table of contents, we're going to do some independent choices. Ideas of an independent choice could be if you're going to dinner and you had to choose an appetizer, an entree, and a dessert. Your appetizer choice wouldn't really affect your entree choice. Then we'll talk about dependent choices, such as filling students into different chairs. Once a student has been filled into a chair, another student can't sit there. So these are dependent choices. We'll talk about anagrams. That's when you have letters of a word and you want to jumble them up. We'll talk about choosing with leftovers. So for example, you might have 10 students and only 3 chairs, so you're going to have 7 leftovers. And we'll talk about cases where you don't have the order of the choices don't really matter. So instead of putting students into chairs, maybe you're putting a students into a committee. And it doesn't really matter if you're the first person in the committee or if you're the last person in the committee. All that matters is if you're in the committee or out of the committee. So really, this is all order matters for the most part. And only this last topic is going to be order doesn't matter. And then the last one with pools, you can have pools either with or without order. So you can kind of go either way. So let's just get right into it. Bismillah. So an example, let me see if I can line this up. A restaurant menu features 5 appetizers, 6 entrees, 3 desserts. If a dinner special consists of 1 appetizer, 1 entree, and 1 dessert, how many combinations? This would be an example of independent decisions. We'll talk about how to solve it. 4 people sit down in 4 chairs. So this is dependent decisions with no leftovers. Bismillah. So we have, sorry, if there are 7 people in a room but only 3 chairs. So this is dependent. Once I choose someone to sit in the first chair, they don't have, that chair is no longer available for person 6 or person 5, but there's going to be leftovers. There's going to be, I guess, 4 leftovers in this question. So we're just starting with identifying the types of questions we'll see on the exam. Then we have, if we have a group of 3 people is to be chosen, so we have a group from 7 people. So we have a group of 3, we have 7 choices. So this is order doesn't matter. Order doesn't matter. I just need to choose 3 people from the 7 to join an orderless group, maybe student council. This one I'm going to call combination. That's the math term we use, combination. Just a combination of students. And this one we give kind of this fancy word, permutation. And not just this one, all the ones where order matters. So if I go back up here, this would also be a permutation question. And then this last one on the top is also permutation. So maybe if I had to write a definition, I would say permutation is where kind of this order matters. And then combination are questions such as people joining a group. So order doesn't matter. We'll solve some problems in a second. This one out. Okay, so symbol independent choices. That's like the very first question we saw. And we see that the fundamental counting principle, if you must make a number of separate decisions, then your primary function is multiplication. Pretty simple. We've all done questions like this before. So let's take a look. We'll start with a restaurant menu has 5 appetizers, 6 entrees, 3 desserts. I want to choose 1 appetizer, 1 entree, and 1 dessert. Let me go ahead and make my solutions in this green. So I have 5 choices for my appetizers times 6 choices for my entree times 3 choices for my dessert. 5 times 6 is 30. 30 times 3, 90. 90, it says how many different dinner specials. You can say 90 different specials or 90 choices. And that's the big idea of combinatorics. Combinatorics is all about choices or combinations. So this is a combination of appetizer, entree, and dessert. I'll use a different color because maybe the screen isn't showing up too hot. But pretty simple question, and these are all independent. Your appetizer choice doesn't affect your entree choice, doesn't affect your dessert choice. How many of the 3, okay, how many ways are there of getting from Alphaville to Gamma or to Gamorburg via Bentacart if there are 3 roads from alpha to beta, and there are 4 roads from beta to gamma? Okay, pretty simple. 3 times 4 equals 12 choices. Okay, this one is for you guys to solve. Go ahead and take a second. And once you have an answer, you can go ahead and push play. And inshallah, watch my solution. So we have blue, black, and brown pants. So that's 3 choices. And then we have white or yellow or pink for shorts. That's 3 choices. And then we have whether or not he wears a tie. So whether or not he wears a tie, that's 2 choices. Either he wears a tie or he doesn't. And the question is, how many combinations? Very classic combinatorics question when they use the word combinations. So I'm going to say 3 choices for pants times 3 choices for shorts times 2 choices for ties. So I'll go ahead and write pants, shorts, and then tie. And you multiply these, you get 18. 18 choices. Okay, not too bad. Those are the classic kind of vanilla flavor, independent choices. Your pants choice doesn't affect your shorts choice, doesn't affect your tie choice. That'd be a great world if that was true. Okay, now sometimes we have dependent choices, and when we're working with dependent choices, the name of the game is factorials, which is a fancy word which means to multiply the number by itself, and then each time you go down by 1. So 6 factorial, use this exclamation mark. That means factorial. Just means 6 times 5 times 4 times 3 times 2 times 1. So when you have dependent choices, the thing to remember is the name of the game is factorials. So let's take a look at an example. So when do we use it? The number of ways to put n distinct objects in order. So that means permutation. Without restrictions is n factorial. Kind of a difficult sentence to understand, but we're going to see an example. 4 people sit down in 4 chairs. So you have 4 people, 4 chairs. How many different seating arrangements? So you can kind of mark up the 4 chairs. And you say, well, I have 4 people. So this is maybe, say, chair 1, chair 2, chair 3, and chair 4. How many choices do I have for the first chair? I have 4. How many choices for the second chair? 3, 2, 1. So this is an example of dependent choices with no leftovers. So in the previous one, all the choices were independent. I didn't have to worry about making less choices for every time I chose because pants, shirts, and ties were all independent. But now my choice for chair 1 affects how many people I have left to choose for chair 2. So this becomes a question of factorials. But still pretty simple. 4 times 3 times 2 is 24. So I have 24 possible arrangements. Arrangements is another word for combinations. Okay, you guys can try this next one out. And when you're ready, you can just unpause the video. So you have 5 Olympic rings, so I might make 5 placeholders. And the colors are black, red, green, yellow, blue. So it's also 5. So again, no leftovers. So the answer is going to be 5 factorial, which is 5 choices for the first one, then 4, then 3, then 2, then 1. I'll put in my multiplication symbols. And I think if you multiply this out, you get 120. The more you practice these, the more you start to memorize the factorials. So 5 factorial, I'm pretty sure is 120. Okay, we're moving along pretty quickly. Next, we're going to anagrams. So anagrams are rearranging letters of a word. So these are dependent. Once I choose which letter is the first letter of the rearrangement, I can't use that letter again. So these are dependent. Once I've made a choice, it affects my later choices. And then this with repeats, I'll explain in a second. So the first example is how many rearrangements of the name Ali? So Ali has 3 letters. I have how many choices for the first letter? I have 3 choices. I can either use the A, I can use the L, I can use the I. Whatever I do use though for the first choice, I can no longer use. So the answer to this is 3 factorial, or 6. Now I see a slightly different thing when I say the name Jill. So the name Jill has 4 letters, J-I-L-L. But the problem is I have repeats. What's the repeated letter? The repeated letter is L. L is repeated. So for this type of question, you might start by saying Jill, 4 letters, 4 times 3 times 2 times 1, which would give you 12, 24. But the problem is 24 is too large. 24 assumes that these 2 L's can be used differently. Maybe one of them is like a blue L, one of them is a green L. So it assumes that JILL is the same as, sorry guys, this is going to be kind of weird, JILL. So there's no way to differentiate these two L's. They're exactly the same. Now if you make them in different colors, then maybe you can differentiate them by color, but in the mathematical sense, they're exactly the same. So this is called, if you did this, 4 times 3 times 2 times 1, it's called overcounting. I'm counting Jill, Jill, twice. I'm counting it once here. I'm counting it the second time here. And in the second time, all I've done is switch the two L's. So if I just do strict mathematics, I've double counted the word Jill. I've switched the last two letters, but I haven't really gotten a new anagram. If I switch the last two letters of Ali, I get Ale. It actually works. So the math, it doesn't know that these last two letters are the same. So how do you correctly count? 24 is overcounting. The way you correctly count, so I'll write it here, correctly. The way to do this correctly would say, take the 24, which is what we got with 4 factorial. So right here equals 4 factorial. And you divide by the number of repeats. So the L is repeated. How many L's do I have? I have 2 of them. So I divide by 2 factorial. Well, 2 factorial is just equal to 2. So the answer is 12 anagrams. So you divide by the number of repeats. If I did a second example, maybe here in the corner, I could say, this one now, puppy. Say, how many combinations of puppy do I have? So I have 3, 5 letters, so 5 factorial. That would be the answer if there was no repeats, but P is repeated 3 times. So because the letter P is repeated 3 times, I divide by 3 factorial. You can imagine that there's lots of times where maybe more than one letter is being repeated. Maybe P is being repeated 3 times and A is being repeated twice. Then I would divide by 3 factorial to account for the P's being repeated. Then I would divide by 2 factorial to account for the A's being repeated. So everything that's being repeated gets into the denominator. Let's see if I can think of an example. There's some examples coming up. So I went ahead and wrote them out. It's good to practice writing them out. Sometimes you just have to do it. So I started with Jill, Jill. Then I flipped the I and the L here. Then I flipped the I and the L here. So I had all the combinations. These are all the combinations that start with J. Then I did all the combinations that start with I. Now I have the combinations that start with L. So these are all that have L, J, then something, something. These are all that have L, I, then something, something. And these are all that have L, L, then something, something. So I have total, I guess, five columns. And when you count these out, you get 12 combinations, which matches, right? Because I said that if you did it with overcounting, you're going to get your answer to be 24. But if you count it correctly, you'd have to divide by 2 factorial because the L is repeated twice. So the answer is 12. So whether you list them out or whether you use this double counting, this repeats, you're going to get the answer to be 12 anagrams. Very important to understand. So we'll go ahead and do some examples. So you have 3 names here, or 2 names and a noun. Abdullah, Asya, and philosophy. Go ahead and take a second. And when you're ready, unpause the video. So I got Abdullah, 1, 2, 3, 4, 5, 6, 7, 8. So 8 factorial, divide by my repeats. It looks like A is being used twice and L is being used twice. So I'm going to divide by 2 factorial for the A's and divide by 2 factorial for the L's. How would I do this in the exam? I would have to go onto the calculator and say 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Plug that all in. And I would divide by 2 times 1, which is just 2. Divide by times 2 times 1, which is just 2. And you would do all of this, and I got 10,080. It's nice to do this in class because then you guys can correct my math, but I think the answer is 10,080. Okay, let's take a look at the name Asya. We got 6 letters, so equals 6 factorial. That's what the answer would be if there was no repeats, but the letter A is being repeated 3 times. So I'm going to divide by 3 factorial. And when I did this, I got 120. And then we can look at the word philosophy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equals 10 factorial. That's going to be a pain to do in your calculator, but nothing that we can't do. And then let's look at the repeats. It looks like P is being repeated twice. It looks like H is being repeated twice. And it looks like O is being repeated twice. You see that these numbers can kind of explode. I got 453,600. Okay, that's anagrams. Moving along quickly. The next topic we have is choosing with leftovers. So in the classic example, 7 people in a room, but there's only 3 chairs. How many different seating arrangements are possible? Let me see if I solved it on the next one. Yeah, I did. Okay, I'll just do it over here. So there's 2 ways to do this. Some people who are kind of in love with the anagram method, they just change this into an anagram. So they say, well, one person gets the first seat, we can give him an F. There's going to be a person who gets the second seat, we can give it an S. There's going to be a person who gets the third seat, we'll give him a T. And then there's going to be 4 people who are left out. So the 4 people who are left out, you make up a letter for them, you can say Z. The last 4 people get Z. So you've changed this problem about 7 people in a room into an anagram, into a word. First, second, third, left out, left out, left out, left out. And then the question is, how many possible choices are there for this anagram? So you say, well, there's 7 letters total, so that's 7 factorial. There's 4 repeats, the Z's. There's no repeats here. The F, S, and the T are not repeats. So you do 7 factorial over 4 factorial. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So you can notice that 4 times 3 times 2 times 1, 4 times 3 times 2 times 1, it's on the top and the bottom of the fraction. So you can just cancel it out. And really what the answer here is 7 times 6 times 5. 7 times 6 times 5, I think, is 210. 210. So that's method 1. Lots of people do this. They call it the anagram method. You take this question and you change it into an anagram. What I personally do is called the choice method. So I say I have 3 chairs. I just make 3 lines. I say, how many choices do I have for the first chair? For the first chair, I have 7 choices. How many choices do I have for the second chair? Well, I've already used one of the people up, so now I only have 6 choices. And you see that you just jump straight to this 7 times 6 times 5. And the last remaining 4 people, I don't have to worry about them. They don't even need chairs. So I just do 7 times 6 times 5, and I also get 210. So this is choosing with leftovers. And it's no different than this slide right here. We have 7 anagrams. This is the anagram method, and this is the choice method. You just make 3 chairs, and you say I have 7 choices, then I have 6 choices, then I have 5 choices. And that's choosing with leftovers. It's not too bad. There'll be more examples on your homework. So let's go ahead and take a look at choosing without order. We call this combination. Combination. I know the whole entire thing is called combination. It's combinatorics. But this specifically is called combination. So you have 3 of 7 standby passengers are selected. So 7 people are standby, 3 of them are selected for the flight. How many different combinations of the standby passengers can be selected? So how many different combinations? So it's not saying, well, who's going to sit in seat 5A and who's going to sit in 24D. You're just saying 3 of them are selected out of 7. So what we'd write in kind of formal mathematics would be 7 choose 3. And the C actually doesn't stand for choose. The C actually stands for combination, 7 combination 3. But you can think of it as 7 choose 3. And this implies, when you see the C, it implies order doesn't matter. Order doesn't matter. I just need to choose 3 people from 7. So if I was going to go ahead, I would say this first number is the number of people, and this is the number you choose. So there's going to be leftovers in these questions. If there's no leftovers, then the question is trivial, right? Because you say, I have 7 people, and I want to choose 7. So 7 choose 7. 7 choose 7. Well, there's only one way to do 7 choose 7. You just choose all of them. I have 7 people that are standby. I have 7 seats. How many ways can I choose 7 from 7 people? We'll just choose all of them. Not a problem. Order doesn't matter. Now, if I'm doing permutations, maybe I'll do that on the top here. permutations where order does matter, I might have 7 permutation 7. Now for combination, the question is really easy. I have 7 people, I just end up choosing all of them. But for permutation, order does matter. So I have 7 people, so this is the number of people, and this is the number of choices or the number of seats. So I say 7 seats, 1, 2, 3, 1, 2, 3, 1. So that's 7 seats. I have 7 choices for the first one, 6, 5, 4, 3, 2, 1. What is this? This is 7 factorial, right? Equals 7 factorial. So if I have 7 people and I have 7 seats and I'm doing something that order matters, there's a ton of ways that I can get these 7 people to sit in these 7 different seats. They can sit maybe the girls in the front and the boys in the back, or vice versa. But if it's just a question of combination, there's only one way. You just choose all of them. I have 7 people. I have a committee of 7 people that I need to make. Well, it's only one option. Take all of them and put them on the committee. But we'll see this with anagrams, which some people love to do all the questions with anagrams. So I would say the people who get standby, I'll give them an S. So there's 3 people who are going to get standby, S, S, S. And then there's going to be 4 people who are left out. So I'll give them an L. And then the question becomes, how many ways can I rearrange these 7 letters? So I would say the number of choices equals 7 factorial, because I have 7 letters total. That would be the answer if there's no repeats. But I have 3 repeats of S, so it's going to be divided by 3 factorial. And I have 4 repeats of L, so that's going to be divided by 4 factorial. And then you solve this. Hopefully I already solved it. 7 factorial over 3 factorial divided by 4 factorial. Okay, it doesn't look like I solved it. That's okay. So 7 factorial over 4 factorial is going to be just 7 times 6 times 5. Why? Because what's left, which is going to be 4 times 3 times 2 times 1, is going to cancel out with this, 4 times 3 times 2 times 1. So I'm going to just stop at 7 times 6 times 5. And in the bottom I have 3 factorial. So I already used the 4 factorial. 3 factorial is 3 times 2 times 1. Well, 3 times 2 is 6. So the 6 and the 6 cancel. So all I'm left with on top is 7 times 5, which is 35. So if 3 of 7 standby passengers are selected, how many different combinations? There's 35 combinations. And that's doing it with the anagram method. So I'd say assign standby to be a letter, I assign it to be S, there's going to be 3 of those. I assign being left out to a letter, that's going to be L, there's going to be 4 of those, and I just do it as a classic anagram question. If you can get lucky, you can not have to crunch as many numbers by seeing what cancels out with what. If not, just do the whole entire numerator, 7 times 6 times 5 all the way to 1. Then do the same thing for 3 times 2, 4 times 3 times 2 times 1. Do the division out. Make sure you don't make any calculator mistakes, but you should get 35. Okay, some formal definitions. You don't strictly need to know these for the test, but they might help. So the strict definition of permutation, NPR, n factorials on top, n minus r factorials on bottom. So how do we think about this? The better way to think about this is R is the number of seats, number of choices to be made, N is the total number of people. We always make a line for every seat. So we make R seats. Then we do N times N minus 1 times N minus 2. And we keep on going down until we get to the last one. What's the last one going to be? The last one's going to be N minus R minus 1. So permutation, you can memorize this kind of funky formula, or you just do it out with these horizontal lines, and you're going to get the same answer. So, for example, let's look at 7P3. 7P3, the classic question that we just did. You have 7 people, you're going to choose 3, and order does matter. So let's say you're putting them in chairs, and the chairs are in order. So you have 3 chairs in order. How many ways can you put 7 people? So I have 7 choices for the first chair, 3 choices for the second chair, 5 choices for the third chair, 7 times 6 times 5. That's the answer. If you want to use the very rigorous formula, you would say, okay, well, that's the same thing as saying 7 factorial, that's the numerator. The denominator is 7 minus 3. So 7 minus 3, 7 minus 3 factorial. So that gives you 7 factorial divided by 4 factorial. We said what happens is everything after 4 cancels out. So all you're really left with is the first 3, 7 times 6 times 5. And everything else, 4 times 3 times 2 times 1, it's going to be the same on the numerator and the denominator. It's going to cancel out. So for permutations, this isn't really that important. Really what you should be looking at is this one. Just write out 3 horizontal lines. That's the number of seats you have to fill, the number of choices you have to make, and then start at 7, start at n, and keep on decreasing by 1 until you run out of chairs. And then for combination, this means order doesn't matter. And the way you're going to do this is you're going to start with the permutation. So you're going to start with what you got here as your answer, and then you're going to do one last step. You're going to divide by r factorial. So if the question was 7c3, so I have a committee. Let me say 3 members. So number of members of a committee. Order doesn't matter. And then number of people. I start by doing the permutation question. So 7p3, which equals 7 times 6 times 5. But that would be overcounting. That would be assuming that order does matter. But since order doesn't matter, the last step would be divide by r factorial. Well, what's r? R is the second number right here, the 3. So I would divide by, so let me see here, 7c3. Let me write it out one more time. 7c3 equals 7p3, 7 times 6 times 5, divided by 3 factorial, which is going to be this, r factorial. So this is the rigorous formula. This one is worth memorizing. And we're going to use it in the next coming questions. The first one, not worth memorizing. Just write 3 horizontal lines, 7 times 6 times 5. And you see in the combination problem, you start with permutation, then you divide by r factorial. So let's go ahead and take a look at an example. I know that might have been a little bit theoretical, but when you see it in action, it's not too bad. So Ahmed has 4 students in class, Zaid, Abdullah, Ibrahim, and Sami, and he wants to pair them up so that they can grade each other's quizzes. How many possible pairs can they make? So I'll go ahead and give you a second to try to write out all the possible pairs. For Zaid, you can use the letter Z, Abdullah, the letter A, Ibrahim, the letter I, and Sami, the letter S. So go ahead and try to write out all the possible pairs. After you're done with that, you can unpause the video. And this is what I came up with. So these are all the possible pairs. Sorry, it might be a little bit not straight. Let me straighten it out. So you have all the possible pairs. So I have 1, 2, 3, 4, 1, 2, 3. So 12 pairs. 12 pairs. But you'll notice that there's some double counting going on. This is called overcounting. This pair says Zaid and Abdullah. This pair says Abdullah and Zaid. But that's the same pairing. They're going to be switching each other's quizzes. So that's overcounting. So I should cross out this one. This says Zaid and Ibrahim, and this says Zaid and Ibrahim. It's the same pair. I should cross that out. Likewise for Zaid and Sami and Zaid. It's the same pair. And you're going to keep on crossing out extras. Sami and Abdullah, that's an extra. Sami and Ibrahim and Sami, that's an extra. And what you're left with is 6. 6 pairs. So these 12 pairs would be the answer if the question was permutation. 6 pairs, that would be the answer if it's combination. So if order did matter, if Zaid Abdullah was different than Abdullah Zaid, then yeah, the answer would be 12. You write out all the possible combinations. But when Abdullah Zaid and Zaid Abdullah is the exact same thing, they're going to be switching each other's quizzes. Order doesn't matter. Then you have to cross out all the repeats, and you're going to get 6 pairs. So for the answer for this question would be 6 pairs. Now if I said, I want to split everyone into groups of pairs, and I want one person to be the leader and one person to be the follower. Now order does matter, because Zaid Abdullah would be Zaid is the leader, Abdullah is the follower. Abdullah Zaid would be Abdullah is the leader and Zaid is the follower. Order would matter, and you would prefer this answer, 12. But because we're just switching quizzes, this is going to be order doesn't matter, 6 pairs. Now you don't want to do this every single time because the numbers are going to start to get very big. So what you really should do is you say, well, this question says there's 4 people, Zaid, Abdullah, Ibrahim, and Sami. You have 4 people. And how many people in the committee? The committee is 2. Two people. So this is n, this is r. So it's 4 choose 2, or 4 combination 2. Well, 4 combination 2 is the same thing as 4 permutation 2 divided by the second number factorial, 2 factorial. Well, what's 4 combination 2? 4 combination 2 is just make 2 lines, 4 times 3. 4 permutation 2. So just make 2 lines and start counting down. So 4 times 3. The bottom is 2 factorial, which is 2 times 1, which is the same thing as 2. So 4 times 3 is 12, divided by 2 is 6. So the answers check out, right? We got 6 when we wrote it out, and we got 6 in the fast way, where we just did the formal definition of combination. And you're going to want to memorize this. So for combination 2, when do you use combination? Only when order doesn't matter. Your numerator is going to be the answer, assuming that order did matter, pretending that order did matter, the permutation answer. And then your denominator is going to be the second number, the size of the committee. These are just pairs, so the size of the committee is 2 factorial. So let's go ahead and do an example. Give yourself a second to do it. When you're ready, you can unpause the video. Okay, so we have choose 5, and there's 8 total. So you could say 8 equals n, that's your number of your friends. Your committee is 5. So this is 8, choose 5. The numerator is always permutation, so I'll say 8p5. The denominator is the size of the group, the size of the committee, factorial, so 5 factorial. Well, what's 8 choose 5? I make 5 seats. I do 8 times 7 times 6 times 5 times 4. 1, 2, 3, 4, 5. Perfect. 5 seats divided by 5 factorial. And I would do this on my calculator. And after I would do this on my calculator, I would get 56. If you want a small shortcut, you could say, well, 5 factorial is 5 times 4 times 3 times 2 times 1. So 5 times 4 is in the numerator and the denominator. So all you really have to do is 8 times 7 times 6 for the numerator. And for the denominator, you have to do 3 times 2 times 1, or just 3 times 2. So these shortcuts save you a few calculator clicks, but if it leads you to making a mistake, maybe just do it out the old-fashioned way. Simple enough. More examples in the homework. The last topic we're going to do, inshallah, is multiple pools. It says it right there. It's kind of small. Right here. Multiple pools. So this is when you have multiple selections. The name of the game is to do the selections separately and then multiply. So do the selections separately, and then step 2 is just to multiply. This is exactly like you have pants, then you have shorts, then you have ties. You do pants by itself, you do shorts by itself, you do tie by itself, and then you multiply. Likewise for appetizers, entrees, then desserts. So these ones are a little bit more complicated, but it's not too bad. So we have 3 seniors and 2 juniors are going to make a committee. There's 12 seniors total. There's 11 juniors total at the school. So I'm going to solve seniors by itself. The number of choices I have for seniors, I'll solve that all on its own. Then I'll multiply by the number of choices I have for juniors, all on its own. So I'm going to split the question into 2. The number of seniors, well, there's 12 seniors total at the school, and it is a committee of 3 seniors. And it's a committee, right? It says delegation. There's no indication that order matters here. So this is just choose. 12 choose 3, 12 combination 3. The juniors, there's 11 juniors, and I need to choose 2 of them. Again, no indication that the order matters. So then this just becomes one of those kind of annoying plug-in questions. Maybe you get lucky and it'll be multiple choice. And one of the choices would just say 12C3 times 11C2. And then you're done. But if it's a question where you have to actually crunch all the numbers, we can handle that. So what would you do? Here, 12C3 is equal to 12P3 divided by 3 factorial times 11C2 is equal to 11P2 times 2 factorial. Well, what's 12P3? 12P3, I just make 3 lines. 12 times 11 times 10. This is equal to 12p3. What's 11p2? 11p2, I make 2 lines. 11 times 10. 11p2, 11 permutation 2. So this one I'm going to say, equals 110. 110 divided by 2, which equals 55. This one's a little bit more complicated. 12 times 11 times 10 divided by 3 factorial, so 3 times 2 is 6. The bottom's going to be 6. And I crunched this all out. What did I get? I got 220. 220. So there's 220 choices for seniors, and there's 55 choices for juniors. So my final answer, I'm going to have to go off the page, 220 choices of how I can choose the seniors times 55 choices of how I can choose the juniors. I multiply these together, and I got 12,100. If you have any question on these, you can find me on campus. But that's how you would solve this. Multiple pools. The first pool is the senior pool. The second pool is the junior pool. Okay, we're right around 40 minutes. 2 questions to go. Go ahead and take a second to solve the first one. And when you're ready, you can unpause the video. Okay, 3 men out of 7, 3 women out of 6 to be chosen to serve on a committee. Order doesn't matter. And how many ways can the committee be formed? So I'm going to say it's going to be the number of choices for men, times the number of choices for women. Okay, so men is going to be 3 out of 7, so 7 choose 3. For women, 6 choose 3. And then if you're lucky, these are the answer choices. The answer choices are in terms of combinations or in terms of permutations. But you might have to solve it out and just actually give them the answer. In which case, you say, well, 7 choose 3 is equal to a fraction. The bottom is always the second number factorial, 3 factorial. Here it's also 3 factorial. The top numbers just change the combination into a permutation. So 7p3, 6p3. Go on the side and solve your permutations. So I'll say 7p3, 3 lines. 7 times 6 times 5. That's 7p3. And then I have 6p3. So that's 3 lines again. 6 times 5 times 4. That's 6p3. And you do the math. You do the math. And then you divide by 3 factorial, which is 6. What did I get? I got this to be 35. I got 7c3 to be 35. That's the number of choices for men. I got 6c3 to be 20. That's the number of choices for women. It makes sense. There's more choices for men. You have 7 of them, and you have to choose 3. For the women, you only have 6 of them. So there's a little bit fewer choices for how many committees of the women. And then again, you just multiply these two. So 35 times 20. The final answer is you have 700 different committees, 700 different choices. Simple enough. Last question. Go ahead and pause. And when you're ready, hit play. Okay, so a pod of 6 dolphins always swim in a single file line. So a single file line to me means order matters. When people are in a line, that's not really a committee. There's someone in the front, there's someone in the middle, there's someone in the back. There's 3 females in the front, and there's 3 males in the back. How many different arrangements can the dolphin swim? So again, this is a classic case of multiple pools. I'm going to handle the males and the females separately. First, I'll handle the females, and then I'll handle the males, and then I'll multiply. So there's 3 females, and there's 3 males. And it says there's 6 dolphins. There's no leftovers. There's 6 dolphins and there's 6 chairs, there's 6 positions that they need to sit in, so there's no leftovers. So I have to just read this question and assume that we have 3 female dolphins and we have 3 male dolphins. You can give them 3 female names and you can give them 3 male names. And amongst the female dolphins, you have 3 choices for the first seat, 2 choices for the second seat, 1 choice, the last one out, is going to be the third seat. Those are the 3 females swimming in front. And then likewise for the 3 males swimming in back, you have 3 times 2 times 1. order does matter, right? So this is a question of permutation. So I could write this out as 3 permutation 3. I have 3 female dolphins. I need to fill up 3 female spots. I have 3 male dolphins. I need to fill up 3 male spots. Well, that's the exact same thing, right? 3P3, make 3 seats, and then write them in 3, 2, 1. 3P3, make 3 seats, write them in 3, 2, 1. So this is 6, and this is 6. 6 times 6. The final answer is 36. So notice that this question is also multiple pools. We're dealing with the males and the females separately, but it's a permutation question. Permutation question. This question up here, multiple pools. Again, we're dealing with men and women separately, but this is a combination question. So in the very beginning, we said this last topic, multiple pools, it can be done, this last topic, multiple pools, it can be done with order, meaning permutation, or it can be done without order, meaning combination. All you have to do is make sure you keep your pools separate. If you look at this last question and you say, oh, well, order does matter. There's 6 dolphins and there's 6 spots. The answer is 6P6. You'll get the wrong answer, right? 6P6 means you make 6 chairs, 6 times 5 times 4 times 3 times 2 times 1. That's not the same thing as 3P3 times 3P3. You're gonna get, this is going to be the wrong answer. So when you have multiple pools, men and women are being done separately, are being taken care of separately, then you have to treat it that way. So solve the question as if it was just talking about the females, solve the question as if it was just talking about the males, and then you multiply them. Okay, while I'm on campus, I'm going to send you guys a homework. Let me know if you have any questions. Assalamu alaikum wa rahmatullahi wa barakatuh.